Hello, welcome to an adventure. How is everybody today? I hope that you are having a good midweek. Whatever time zone you're in, good zone. If you are unfamiliar, I am Anthony Wright Day Hernandez, the Community Collections Archivist here at Virginia Tech. You may know me online as Rogan27, and this is a weekly show that I do where I share materials from special collections and university archives here on Twitch so that you can explore them with me. It is a, yeah. I don't have more to say. That's it. That's the intro. I was like, I feel like I'm supposed to continue, but then my brain didn't know what to say. Hi, Hannah. Got your caffeine a bit early today, so you'd actually be here for the entire stream, barring a customer coming in. Thank you very much, Hannah. Your assistance has definitely been appreciated in helping to, monitor the chats. So how about we just dive in? I have plenty of stuff, and there's no way we're going to get to it all. So I should not get distracted. I say as I get slightly distracted, although not like totally distracted. We're going to start, as always, with the land acknowledgement and labor recognition. Virginia Tech acknowledges that we live and work on the Tutelo and Monacan people's homeland, and we recognize their continued relationships with their lands and waterways. We further acknowledge that the MORL Land Grant College Act of 1862 enabled the Commonwealth of Virginia to finance and found Virginia Tech through the forced removal of Native nations from their lands in Western territories. We understand that honoring Native peoples without explicit material commitments falls short of our institutional responsibilities. Through sustained, transparent, and meaningful engagement with the Tutelo and Monacan peoples and other Native nations, we commit to changing the trajectory of Virginia Tech's history by increasing Indigenous student, staff, and faculty recruitment and retention, diversifying course offerings, and meeting the growing needs of all Virginia tribes and supporting their sovereignty. Virginia Tech acknowledges that its Blacksburg campus sits partly on land that was previously the site of the Smithfield and Solitude plantations owned by members of the Preston family. Between the 1770s and the 1860s, the Prestons and other local white families that owned parcels of what became Virginia Tech also owned hundreds of enslaved people. We acknowledge that enslaved Black people generated wealth that financed the predecessor institution to Virginia Tech, the Preston and Olin Institute, and they also worked on construction of its building. Not until 1953, however, was the first Black student permitted to enroll. Through inclusive VT, the institutional and individual commitment to prosim, that I may serve. In the spirit of community, diversity, and excellence, we commit to advancing a more diverse, equitable, and inclusive community. As always, we like to take a look at those at the beginning of the stream, since we're going to be looking at history stuff, and that's institutional history right there. I stumble a bit sometimes because they are not worded how I would choose to word them, and I think some of it could be improved, but it has evolved over time. Anyway, how about we take a look at what I have selected for today, making sure I have the things selected properly before I switch screens. Huzzah! Okay. For today, we're going to take a trip back to the 1950s primarily. The actual date range for this collection is 1936 to 1996. But we're going to be exploring the Paul R. Hill collection. And so let's take a look at this biographical note here, because Paul Hill, probably not somebody that you have necessarily heard of, definitely not somebody I had heard of, but Paul R. Hill, born 1909, died 1990, was a renowned NASA engineer and UFO enthusiast. He received his Bachelor of Science in Mechanical Engineering from the University of California at Berkeley in 1936. After teaching at the Polytechnic College of Engineering in Oakland, California, Hill began his career with the National Advisory Committee on Aeronautics, NACA, which was the predecessor of NASA, which, of course, it goes on to say here. He began his career with NACA in 1939, which became NASA in 1958. He worked at NASA until 1970, where he published numerous scientific and technical reports. Hill was also an adamant UFO enthusiast. Based on his own personal sightings in 1952, Mr. Hill tried to use his scientific and engineering knowledge to understand how UFOs worked and eventually built his own flying platform. His book on the topic, Unconventional Flying Objects: A Scientific Analysis, was published posthumously in 1955. Posthumously, to my knowledge, does not normally have a hyphen, which caused me to stumble. But Mr. Hill was married to Frances Hoback Hill, who died in 1999. They had one daughter, Julie M. Hill. Hill, referring to Paul, this sentence, died in 1990 at the age of 81. As always, when we read through finding aids, I trip over things that I would do slightly differently. I don't think anything here is wrong, necessarily. I do question a hyphen in posthumously, and there's a little ambiguity with the final sentence there, following after Julie M. Hill, and then it says Hill died in 1990, which somebody, and indeed when I started reading it, I was like, wow, their daughter died too? But it's referring to Paul Hill. So there's some ambiguity that could be cleaned up. But generally, the biographical note there gives some good information. Can confirm there should not be a hyphen, at least according to Merriam-Webster. Thank you, Hannah. So what this collection has is material relating to the NACA/NASA Langley career of Paul R. Hill. Materials in, I'm opening my water bottle wrong, sorry. Materials include books, papers, newspapers, lantern slides, NASA publications and memos, overhead sheets, and notes from presentations and tasks. There are photographs of Hill's design for a personal flight device, and other drawings reflect planetary orbits or space station models. So the focus, and what I was hoping to focus on with this collection today, is the research and development that was done at NASA Langley, specifically on space stations, and also Paul Hill's research into interstellar flight that was done for NASA. But as always, anything, so I have the whole collection here. So if you see something listed in the container list, if you pull up the collection and you see something in the container list and you're like, ooh, what is that? Or that sounds amazing. Or I know what this is and it's cool, and you want me to show it on stream, let me know and I will grab it and we will look at it. Hi, Conciliance. The music is slightly loud. I should be able to adjust slightly. I hope. I just don't want there to be no background music, because then I think it gets a little not great. So yeah, container list is available live on the Finding Aid online. Take a look. If you see something and you're like, we need to look at that, let me know. Otherwise, I have identified a couple of topical highlights and jotted down notes telling myself where they're located, so that I can sort of jump over some of the less interesting things and go to the slightly more interesting things. So how about we start taking a look at stuff? We are going to start today. It's better now? Awesome, thank you. We're going to start today with the lantern slides that were mentioned. There aren't very many of them. I just need to get this light box on. We've done this before, multiple times. I do not know also what order these are meant to be in, so we'll find out together. But I had a moment right before stream where I was like, do I really need to take those, like, do I really need to go and grab the light box, or can I just leave the lantern slides here? And then I started looking at the lantern slides and I was like, no, these are pretty cool. And they're not like, well, you'll see. This one is broken, so I'm going to try and not cut myself on shards of glass while still attempting to place it in a space where you can see it. Ha-ha! Success. Let me zoom in a little. Right. So, part of the work that Hill was doing was developing space stations at NASA Langley. Like, planning for, it is transparent, yes. It's a slide. It's a lantern slide. So yeah, it's transparent. At first you thought it said Star Labs and were worried that the flash was going to show up. It's space laboratory requirements. Minimum assembly in space is the first requirement. So for a space lab, there needs to be minimal assembly once it's up there. 2, power plant incorporated continuous. So onboard power generation that works nonstop is what I read that as. Needs to be adaptable as a booster payload. So there needs to be some flexibility or adaptability in attaching it to a rocket to shoot it into space, is what that means. Space laboratory makes a lot more sense. Yeah. Let's see. 4, rotation. A, rotate for artificial gravity. B, not rotate for 0G and scientific observation. And C, dynamically stable about axis of rotation. I'm hoping that some of this gets slightly further explained as we look through documents, but they need to be able to rotate the laboratory for artificial gravity to generate a like using the centrifugal force to simulate gravity, something we are generally pretty familiar with today as a concept. They needed to be able to halt the rotation in order to do 0G in order to do things in 0G and to do scientific observations. But it needs to be dynamically stable about its axis of rotation, so it needs to not wobble from side to side as it's rotating around its axis. So that seems like a reasonable requirement. 5, taxi available always. I presume that means that for a space laboratory to be viable, transit to and from needs to always be possible, so that if people are at the laboratory, they could always make it back to Earth. I'm not certain, that's my guess, as to what that means. Hopefully we will find answers to some of these hypotheses as we move along. 6, communication, two-way television. So two-way video communication required. 7, reliable boost system. in order to have a space laboratory, apparently they needed reliable rockets or a reliable way of getting things into space. That makes sense. 8, unallocated space. I think that also makes sense. If you're going to put a laboratory up there, you need somewhere up there that's not already spoken for. And 9, reasonable life. This is not, this is product lifetime sort of life. It needs to last long enough to make it worth putting up. So that makes sense. Oh, welcome back, 123 Ricardo 210. I think the boosters may have to do with keeping orbit. That's possible. That is a good hypothesis. And we'll learn, because I don't know, but I do know that there are multiple documents that I've marked for us to look at that are focused on the design requirements for space stations. I'm just going to put the shards of glass back on the slide here and then cover it with the foam again. This was the only broken one, and this is the most broken lantern slide that I have ever encountered in looking at lantern slides on stream. So, all right, let's see, what's this next one? Ooh, space laboratory specifications. So these, to me, look like presentation slides. They're just glass plates that are meant to go in front of a light projector to be displayed on a wall. So they're not even like the little cardboard holding a piece of film type slides that go in slide projectors that that a lot of people would be really familiar with. These are older, and if you want to know more about glass lantern slides, we explored the history of the technology on a previous episode last year, which is available on the library's YouTube channel. Space laboratory specifications: 1, orbit, circular, altitude. The circular orbit altitude of 400 miles. Station life, 1 year minimum. Number of people, 2 minimum. Rendezvous cycle, 30 days. Food, water, and supplies, 60 days worth. Artificial gravity, 0 to 0.5 G. Power plant, solar fluid cycle, 8 kilowatt continuous. I'm not certain what that means. Like, solar power makes sense. I don't know what fluid cycle in this context means. If somebody does know, feel free to share. Otherwise, that'll be something I'm looking to learn as we look through the materials. Pressures, oxygen, partial at 3.1 psi, and then total pressure of 7 psi. Atmosphere, Smithsonian number 2. I'm curious about the atmospheric mix, and that it is called Smithsonian. That is, I've not encountered that before. I'm very curious about that. This one I'm curious enough about, I'm gonna do a quick search and see if I get a result right away. I'm not getting results that answer my question just from a quick internet search. So this is another thing that I'm going to either need one of you to find for me and share, or I'll look for it as we go along. When you try and look it up in connection with a power plant, it comes up with, fluid cycle is similar to fluid power. So fluid power generation, I would think, is similar to like a heat exchanger type power generation, where it cycles from the interior to the exterior and would generate power through the heat exchange, but I'm not certain. That's where my brain goes with that, but I don't know. I'm not, like, fluid power, I guess I don't have a good definition for personally. Thank you. Thank you for putting a definition in the chat. The use of fluids under pressure to generate, control, and transmit power. Okay. Fluid power is conveniently subdivided into hydraulics using a liquid such as mineral oil or water, and pneumatics using a gas such as compressed air or other gases. Got it. So I would take it as solar power generation with fluid power for transmission would be my guess, since it listed both of them. So, of course, all of this work was done in Langley, Virginia, at the NASA Langley Research Center, their space laboratory effort. So, Langley Research Center research, space laboratory objectives, let's see, configurations research, space frame research, systems research, space laboratory operations study. So they wanted objectives and then did research on this is like a workflow, it looks like. Research on configurations, space frame research, systems research, space laboratory operations study. And that was the plan for the Langley Research Center, MSC. MSC. Is that the Manned Spaceflight Center? Yeah, so it was the Manned Spacecraft Center. Today it's the Johnson Space Center. It's Houston. So Houston on this project, environmental control systems, basic space frame, logistics, spacecraft, operations. And then the next step, they take the results of Langley's research and combine it with the results of their research for Manned Orbital Space Laboratory. And they incorporate the launch vehicle, space station. Interesting, okay. They're also pulling in, let's see, NASA use, research and development experiments in space, and operations integration. Okay. So workflow on the space laboratory effort. That's a very broad level, like high level, like project description there. Let's see. Ooh, stability criteria. These are neat looking little slides. I'm sure there's probably more context in the documents as we get into them, but stability criteria, mathematical formulae that, sure. I don't know what okay. The double greater than sign, what does that signify? I'm not a maths person generally. Used for an approximation of the much greater than sign. Okay, so the two greater thans means much greater than. So I sub z is much greater than I sub x, which is equal to I sub y. Stable, I sub z is much lower than I sub x, which is equal to I sub y. No stability, I sub z equals I sub x equals I sub y. Oh yeah, that's just gonna go wherever it wants. And unstable, I sub y less than I sub z less than I sub x. I think I in this case is inertia, but I don't know. But that would make sense to me, that controlling inertia affects the stability of an object in a zero gravity space. Wow. Rational parameters and human factors. Radial angular velocity, percent change in gravity head to... I do not know exactly what this one is showing us. I think it is just showing the comfortable range of change in feet per second for human bodies. So they're trying to calculate the the spin and the angular momentum of the station in order to calculate and figure out what will be comfortable for a human, it looks like. I don't know. I love that, like, as we dig through, I do believe that there will be documentation that will probably provide us more information for these graphics. I love starting with the graphics and just being like, here's my speculation. Especially as a not scientist. My only science, my main science education is library and information science, which is definitely not space science. Radial acceleration and gravity units. So this is just a detail from the other chart that we saw. External environment compatibility. Are we going to matchmake for external environments? Here's our compatibility profile. Radiation. Ultraviolet high energy particle radiation of 200 to 4,000 angst. A. I have no idea what A is. What is the unit? Oh, UVA radiation? Is that what it's meaning? No. Yes? I'm trying to find out. I think it might mean absolute. here we go. No, it is referring to UVA. Or no, it's not. It's not. I thought it was. But then I clicked into it and I was like, nope, it's not. Unit of measure. What is the unit of measure for ultraviolet radiation? So normally it's milliwatts per square meter. Huh. So I'm not 100% certain what the A is for here. The closest that I'm seeing as a possibility, the thing that makes the most sense to me, is that it would mean absolute, but I don't know for certain. Let's see, orbit, inclination of 28 to 33 degrees, altitude approximately 300 nanometers, eccentricity of less than or equal to 0.01, so 1%. Don't ask me, I'm an artist, not a scientist. Hey, yeah, I'm not asking, I'm just saying I'm done searching for now, and I will leave that as an open question. If we find it in the documents later, great. That's one that I'm not able to find an answer quickly. External environment compatibility vacuum. 1 times 10 to the negative 8th millimeters Hg? Again, not a space scientist myself, but I'm curious. Hg in measurement of vacuum. Huh. The common standard to measure rough vacuum is inches of mercury, which is what the Hg is referring to. So, what is the atomic symbol for mercury? Oh, I did not know that mercury was Hg, which is why I didn't get it. Hg is on the periodic table of elements. That is the symbol for mercury, is Hg, and I was not aware of that. I know a lot of them. I did not know that was mercury. Quick search. A bar on each side is the symbol for absolute. So not sure. Yeah, I have no idea what the A is trying to signify here. External surface temperature of minus 50 degrees to 150 degrees Fahrenheit. Meteoroid environment. Interesting. Space station objectives. This will take less, this will be easier to understand than, I do not know what this mathematical abbreviation means. Learning to live in space. Artificial gravity experiments, zero gravity experiments. Applications research, communications experiments, Earth observation, systems research and development, launch platform experiments, and scientific research. Okay. Space station guidelines, natural stability, damping and control. Damping. They want inertial dampers. Rendezvous, dock, abort capability, crew capacity max of 21 and 42. Power generation variable demand, external environment compatibility, lifetime lifetime 1 to 5 years, low leakage. Sorry, just the fact that it says damping was humorous to me because I know I was watching Eric Campbell the other day, who regularly rates this program, discussing the terminology of Star Trek and the lack of consistency between calling them inertial dampers and inertial dampeners in Star Trek. And here we are, a slide from 1962 from NASA, where they are dampers. Space station guidelines, human factors compatibility, shirt sleeve environment, and regenerative life support. Range of gravity capability 0 to 1G, large rotational radius. Unitized structure, launch vehicle, payload compatibility, and automatic deployment. Those all seem reasonable to me. You don't want people to have a spacesuit on while they're there. It should be, once they get there, they can, move around. It might be chilly enough that they'd want clothes, but it's a professional environment, so they're gonna want clothes anyway. Regenerative life support, you don't wanna have to keep injecting volatiles into the life support system in order to maintain it. A closed loop regenerative, like a fully enclosed biosphere in an artificial space, has never been achieved by humans. We need the addition of additional volatiles. We always leak volatiles when we try to do, so we can do regenerative life support up to a certain percentage, but then we leak and have to recharge. Gravity 0 to 1G, that makes sense. And I love the automatic deployment. Yeah, you just want to be able to have it set itself up. I wonder what font or typeface. I don't know. Yeah, I don't know. These are official NASA publications from 1962. So it's whatever typeface NASA used in 1962. But that was the last of the slides. I thought the slides were, yeah, it was a nice, I'm used to things, like older things, like 50s, 60s, stuff like that, being serif, like Times Roman or things like that. I'm less used to them being sans serif, and that was definitely a sans serif font. I'm moving the light box out of the way because I don't need it as we go to look at documents. All right, so those slides were about space stations. So I think we continue with space stations. But I do want to try and so I also have interstellar flight on the list and lunar jet transport as topics to peruse. Box 2, folders 3, 6, 9, 10, 12, and 13. All right. 3, 6, 9, 10, 12, and 13. And box 5 folders 10 and 11 are the ones that I have identified as space station focused. 5, 5, 10, and 11 are image folders, so I definitely also want to pull those. Whew. All right. You want to start with images or documents? So I've got topics covered by these folders. I have, so I have the photographs, of course. Looks like the font is called Microgramma. Cool, thank you, Concilians. So I have spin stabilization. I have spin stabilization history talk and figures for June 1st, 1967, which could be interesting. It's more slides, but they're different slides than the ones that we just saw. And it looks like there might be some notes as well. Not certain. Or it might be just space station history talk. Space station review group correspondence. Meteor reentry life support. I'm not certain why that one's on the list. Space station information. And space station information. How about we start with space station information? Oh, microgramma was also used in Star Trek and Alien? Oh, that's neat. I am going to do something I don't often do on this stream, which is I am going to put on the white gloves. Because, and actually I may have to pull the light box back. I don't think I'm going to need to, because I think the onion skin will obviate the need for the light box, but all right. So this is one of the 2 space station information folders. Oh geez. I'm like, hey, take a look at this. Yeah, I should maybe zoom out, since these items are bigger, and you won't be able to see them at the zoom level that the glass slides worked at. See, I don't know that I actually need the gloves, because I think these are transparencies for an overhead projector, rather than like photographic materials where the gloves would definitely potentially cause harm. But the gloves also probably won't hurt. There aren't like frayed edges of pages that are gonna catch and tear on the gloves. So, MORL section view. What do we have? Common bulkhead, airlock door, resupply or ferry, docking cone, hangar, experimental area, crew living area. Huh. Centrifuge, auxiliary airlock. Very curious. And part of what I'm curious about is, do I have information in the information folders that explain these things to me? Ooh, that looks good. I think we'll look at that here in a second. Yes! I have found an explanation. Based on the size of the humans that they drew, it's huge. Yes, indeed. It is big. This is the short version, according to the handwritten note at the top, where it says, short version. Manned Orbital Research Laboratory, MORL. I'll let you continue looking at the illustration, and I will read to you what this says. One of our ground rules is to minimize interference with the Apollo program. This means the stable of planned NASA boosters and planned logistics vehicles should be used, which are not a part of the Apollo program. The Saturn C1 will drop out of the Apollo program and would seem to be a suitable booster for a small station. The Gemini, with its Titan II booster, would seem to be a suitable ferry for the crew, and the Atlas Aegina for equipment resupply. All these systems should be fully developed in time for the station. The first view graph shows a picture of a small manned orbital research laboratory in the launch configuration. For comparison, we show the Apollo system on the Saturn C1. I don't know if I have the view graph that they refer to. I will check really fast and see if it is included in here somewhere. Doo-ba-doo-ba-doo, doo-doo-doo-doo-doo. I don't know. Let's see. That's launch cones, requirements. Don't. Okay, are these all backwards? I'm going to leave the graphic up. I'm going to read the short description. Then we'll go through these, because I think that will be less confusing. So it's referring to some graphics. I don't know where those graphics are, because not my presentation. And I've not read through this before. I just glanced in the folder and was like, ooh, this looks interesting, and wrote it down as, hey, this is interesting. Here's the Apollo and the Apollo service module. The ORL we have studied is the same size as the Apollo service module, a 13-foot by 20-foot cylinder. The lab is launched without the crew, and the 4-man crew is brought up later in 2 Geminis. The next view graph shows the orbital configuration we have studied. This is the outline of the laboratory, which is still attached to the Saturn IV stage of the Saturn, which can be used as a counterweight in gravity experiments, or if gravity experiments are undertaken. 2 Gemini ferries are shown docked in the normal Gemini manner. It's not referring to this graphic, but I think we've got part of that at least reflected here. The crews come out of the Gemini doors and enter the space station airlock. These are the solar cell power plant arrays, which can also be seen here in the end view. And here's the Agena resupply vehicle. So this is the Agena research supply. I don't see on here the write-up here refers to the solar panels, but I don't see those on this graphic. It's a sketch to show a possible internal arrangement. The interior is divided into 2 rooms. For weight economy, on the initial launch only, the lower compartment is shielded against the beta radiation prevalent at the 200-mile orbiting altitude. In shielded compartment is the command post and bunks, so the crew living area. The power regulation system and the control system. In the other compartment are complete life support system, including the food preparation and eating center and the airlock, which for safety reasons communicates with bathrooms. Let's see. The top is a cable system, as might be used as an artificial gravity backup system. By using the last booster stage as a counterweight, the system could be rotated to obtain artificial gravity to test the crew before re-entry. Okay. Let's see what we can learn by looking through these slides. And I'll put on a glove if I need to. The Manned Orbital Research Laboratory. Space station requirements continued. Okay, let's start with space station requirements. Human factors, automatic deployment, rigid efficient structure, natural stability, automatic damping and control. We saw a lot of these on the glass slides, which is why I'm zooming through them somewhat quickly. Shirt sleeve environment, regenerative life support, reliable power, payload booster compatibility, low leakage rate, rendezvous dock abort capability. Objectives. Learning to live in space is one of the objectives. Communications. I believe this is Earth observation. Zero gravity. How long? Artificial gravity. What level? Because this was before they had really spent a bunch of time in space, right? I don't know the exact date on these slides, but like, they didn't know how long could somebody live up there in 0G. Learning to live in space seems like a pretty important thing. Indeed it does. What do we got? Aha! So this is orbit configuration. We've got the Manned Orbital Research Laboratory, of course. The Agena research or resupply vehicle attached here, and then the solar array, which is on the side. It looks like it's just on one side. And if it's stowed, they've got a dotted line here to represent the solar array being stowed. So it looks like just a solar array here on the side. The 2 Gemini pods, which carry 2 people each. And that is how the crew gets up there, and that's where they would stay docked while the crew is on board. And then the Saturn IV stage that remained attached to provide counterbalance in order to assist in the generation of artificial gravity. as was described in the paper. So that all makes sense and seems like a fairly efficient design for the Manned Orbital Research Laboratory, given that it was using existing technology, basically. It's warm in here, but I can't have the fan blowing the engine spin around, so. Orbital 0G configuration. Look at this, sorry. Look at this art. Look at this artwork. NASA has always had really good artists. So this is the same thing we were just seeing. This is the Agena, the resupply vehicle attached here at the front. These are the two solar arrays. These are the two Gemini. And this is the Saturn IV stage. I think these are really cool. Oh, this is the same slide, or the same transparency. Okay. Launch configuration. I mean, it's all stacked up to look like a rocket. Yeah. So there's a fairing at the top, and then there's the Orbital Research Lab, the Saturn IV stage, which will remain attached, and the Saturn I stage, which will be jettisoned during the launch process. Just checking my timing of things, because we still have plenty of stuff to look at. Woo. So using Saturn C1 and Titan II, as well as the Atlas with the Agena D. Leaving the Apollo rockets free for the moon, the moonshot program. Which, honestly, I did not know that they had done all of this, like, to try and repurpose all of those old pieces of equipment. I didn't know that was a thing. It makes sense, but I didn't know that they had done that. I'm gonna put these back in their folder. There's more in the other folder for us to look at. That is also just... I'm excited. I'm slightly excited about looking at this stuff. And I'm trying to restrain it. So we have, first off here, 1962, July 13th, 1962. We have a document, Space Station Requirements. That just seems like a thing that we should look at before looking at the photographs of the space stations that they built. So this is a rough draft, according to the first page here. Space Station Requirements, July 13th, 1962. The present LRC Space Station Research Program was Langley Research Center Space Station Research Program was initiated to establish the technology necessary for the eventual realization of such a vehicle. This program has been in progress since 1960 and has consisted mainly of in-house efforts supplemented by contractual efforts with industry. A substantial technical background has been achieved which should help establish the sound approach so necessary for carrying out any large vehicle program. It is therefore believed timely to disseminate the accumulated information. In order to orient, plan, and guide our own space station research program, Langley deemed it necessary to carry out the conceptual design of a space station to uncover the problem areas inherent in such vehicles. The carrying out of a conceptual design is, of course, made the more difficult by the many possible configurations that must be considered and types of equipment that could be employed. In order to make conceptual designs and orient research, it is beneficial to have some rational requirements or guidelines, which in turn depend on the objectives. I will therefore briefly discuss some space station objectives and the guidelines that we have evolved and used as a yardstick to measure the degree of excellence of different concepts. For this purpose, let us define a manned orbital space station as a vehicle in which man can live and work in orbit for sustained periods of time for whatever purpose. No matter what the final objective uses of a space station turn out to be, it is clear that first, the environment must be such that man can live and work here or there for sustained periods with reasonable comfort, efficiency, and safety. Every day that passes, man will learn more about his environment and adapting himself to it. Hence, we soon come to our first objective, learning to live in space. To learn most rapidly, he should obtain a variety of experience. And I'm just going to read the text as it's written, unless I come across really egregious things. The convention of always referring to he as the general was very much in full force in the mid-20th century. If you go further back in time, it is not a convention of the English language, and it is starting to be used a little bit less today, but is still also somewhat common today to use the masculine pronouns to refer to the general. But indeed, yes, historical terms. So I'm just going to point it out. It's not generally an offensive form of terminology, so I'm just going to read it as is, but I did want to point to it. Hence, it will be beneficial from this viewpoint for the station to have multiple uses and capabilities. One of the most basic questions with regards to living space, and the one usually encountered first when considering space stations, is, should the space station operate at zero gravity or with artificial gravity? It is a question no one positively knows the answer to. The zero gravity station looks the simpler, yet we know that zero gravity forces causes a number of problems, either of a medical nature or of an inconvenience nature. Some of the medical problems are vestibular disturbances or canal sickness, impaired blood circulation, and impaired muscle tone. Some of the inconvenience problems of living and working in a zero gravity environment are locomotion difficulties. Special assistance devices such as cables, nets, or jet tugs are required. Apparently there are slides that go with this, but I don't know which ones they are. 2, use of hands. Under these conditions, the hands are not altogether free from any tasks, such as carrying things. Also, the exertion of large torques and forces by the hands to do work require that the body reactions be restricted in some manner. 3, floating objects. Floating and loose objects other than on a momentary basis are probably intolerable from a safety viewpoint. 4. Handling of fluids, as in the disassembly of machinery containing fluids, is generally difficult, requiring special equipment. 5. Convection. The lack of natural convection means that all equipment must be cooled by forced convection, people too, and one failure can cause a chain of failure events. 6. Feeding. No steak and coffee on the table. I'm sorry. Everything so far has been so matter of fact, so scientifically presented, just a listing of the potential problems. This one, instead of the food would float around and we'd have to come up with some way for people to eat it, as they wouldn't just be able to put food down on the table, instead of just a general statement of you can't put the food down on the table. Specifically steak and coffee. Which just struck me as really funny for a moment. Apparently they were concerned about their steak and coffee. Almost surprised they chose not to simulate gravity. Honestly, I agree, Ricardo. It seems like they were making a fairly good argument for why gravity, artificial gravity on the station would be needed. While we can design various pieces of onboard equipment to aid people at zero gravity, we cannot really know how they will fare until sustained trials in space have been made. Hence, we come to our second objective, gravity research. Much long-range research at zero gravity must be undertaken to determine how long man can survive at zero gravity, and to learn the effectiveness of shakers and vibrators or other exercise devices in combating any deterioration of the cardiovascular system and general muscle tone. It's a bold assumption that people like steak and coffee, especially at the same time. I agree, Hannah. The advantage of artificial gravity is that it overcomes the problems of zero gravity, bringing the astronaut and all equipment closer to an Earth-type environment. In effect, it relieves the astronaut of some of his burdens and places the burden of work in understanding the use of artificial gravity on the research laboratory. We have accepted this challenge in the shaping of our research program. But of course, artificial gravity introduces new problems. The rotation needed to create artificial gravity introduces a set of rotational parameters to be considered, such as rotational rate and rotational radius. The interrelations between these rotational parameters and the crew are illustrated in a slide. But I don't know what slide. I don't see slides that seem like they fit what's being said here. Yeah, I don't see whatever slides it is saying we should see. If they're here, I don't know where. There are images and things, and we'll look at them, but the ordinate and abscisse of this plot are logarithmic scales of rotational radius and RPM. It's explaining a chart that we can't see. Yay! Lines of constant rim speed and lines of constant fractional gravity. Values given at the top of the figure. The main feature of the chart is the estimated comfort zone. Hey, we saw that. Estimated comfort zone. We saw that in the glass slides, which is similar to others found in the literature on artificial gravity. It is, Ricardo. It is one of the glass slides that we looked at earlier. Let's see. Only 2 or 3 comfort zone limits need concern us at present. One is the 20 feet per second rim speed cut off below which the difference in gravity between walking or standing is greater than 10 to 15%. This is the Coriolis acceleration we hear so much about. Based on airplane and centrifuge experience, larger changes than 10 or 15% may cause one to feel uncomfortable. Expressed in other terms, above and to the right of this line, the effect of the Coriolis acceleration on the occupants is negligible. The second is the I don't know what that is supposed to be. It looks like WXW, but the W, I believe, is meant to be italicized as though it is a Greek letter, and I'm not certain what Greek letter that would be. I'm going to bypass the mathematical notation and just continue reading. The second is the whatever boundary shown here on the 4 RPM above which, based on various centrifuge experiences, vestibular disturbances may appear. The WXW thing refers to turning the head about 2 perpendicular axes simultaneously. The third is a value of 1 Earth G, which would seem ample. There's really not much experience to show that Coriolis force, defined as WXV. But it's not just that they were typing on a typewriter with no W key, right? No, the W key works. So it's definitely an italics W. So I don't know what. Anyway, if I really needed to know for whatever reason, I could always research that further. But I'm gonna move on. Is very, let's see, really not much experience to show that Coriolis force is very important, but there's a lot of experience to show that if one rotates his head rapidly about 2 axes simultaneously, it causes unpleasant sensations. I might hasten to add that one can rotate much faster than this while sitting quietly, as when reading without any sense of being rotated. Also, glancing about with eyeball motions has no effect. Sizing the station. 2 horizontal dashed lines are shown in figure 1, one for a 50-foot and one for a 75-foot radius. It's noted that the 50-foot radius station missed the estimated comfort zone altogether. The 75-foot radius intersects the comfort zone from 0.17 to 0.4 G, which would seem practical in that it duplicates lunar G at the lower RPM and gives a range of gravity in the comfort zone. This radius also gives a percentage change in gravity from head to foot of less than the 10 to 15% mentioned in the literature on artificial gravity as a value believed by psychologists to be acceptable. The conclusions from this chart are that a station in the general neighborhood of a 75-foot radius is needed. This is a direct argument against the choice of a smaller or compromise station which does not satisfy the rotational and human parameter relationships. Hence, Langley has established this approximate figure as one of our research guidelines. Of course, the actual limits of the comfort zone are not presently well established, and probably will not be before experience with an adequate space station has been obtained. The comfort zone boundaries in this chart were based largely on the widely known centrifuge data from Johnsonville, Pennsylvania and Pensacola, Florida. There's considerable room for disagreement in conclusions from ground experiments. In fact, Langley's own work will be reported later by Mr. Stone, indicates W by W requirements more stringent than those for untrained people, and that practice and adaptation moves the boundary out to revolutions per minute. Oh, Whimsies, welcome in. Hi, Mobius Tempest, how are you? 16-bit Eric, thank you so much for the raid. Welcome, Whimsies, to Archival Adventures. I am Anthony Wright Day Hernandez, Community Collections Archivist at Virginia Tech, also known as Rogan27, since that's the channel that you're on. And today's Archival Adventure, we are looking at materials from Paul R. Hill, an engineer with NASA Langley Research Center. And these materials that we're looking at, hi Sonar Fade. These materials are focused on NASA's work in developing a space station, as well as NASA's research into interstellar flight. So right now, we're looking at a rough draft of a paper defining requirements for a space station. This is from July 13th, 1962. I have photos of mock-ups that they did that we'll look at after this, and then after that, I'm going to want to pop over and take a quick look at the stuff on the interstellar flight, because 1960s, they were already working out mathematical and human requirements of interstellar flight. So that's what today is. And yes, the finding aid, if you want to take a look at the finding aid, you could get some historical information about Paul Hill, whose papers these are, as well as see a listing of the things in the collection. And if there's something listed that you think sounds amazing and you want to make sure that I share it, please drop it in chat and I will happily do so. The W is probably an omega symbol, but not sure what that means as far as the math is concerned. Yeah, I don't know either. Omega by omega, that I suppose could make sense as far as naming convention, but means no more to me than W by W. That's their boundary, as explained earlier, for parallel changes in rotation. Turning the head about 2 perpendicular axes simultaneously. So 2 perpendicular axes. And if you're turning the head on 2 axes at the same time, they were determining that you wanted to do that below 4 revolutions per minute. Otherwise, vestibular disturbances may appear. In mathematics, particularly in set theory, the Aleph numbers are a sequence of numbers used to represent the cardinality or size of infinite sets that can be well ordered. Great. Those are words, and they did not make perfect sense to me, but I'm not going to dwell on it because we have plenty of other things to look at. They can... and you don't understand it either. Yeah, I mean, basically, it's saying they can be used to represent the order or the size of a set of numbers. Applications research. There's a great interest in applications research. Let's see. Communications. Man would add greatly to the versatility of advanced communication systems by being able to change the test setup in various numbers, such as changes in frequencies, bandwidth, antenna selection and pointing, coding methods, etc. Also, since new systems are prone to failures, the presence of men who could replace defective electronic parts, either in the space station or in monitored unmanned communication satellites, would greatly increase systems' reliability. Earth observation. With a manned system, the percentage of small area observation to large area scan would be favorably increased because of the human capabilities of selection and discrimination. Using photographs, the losses in transmission are avoided with onboard analysis. Only selected photographs would be transmitted to Earth, thus obtaining a reduction in data handling. Launch platform experiments. The space station with its crew of trained astronauts and technicians would be a suitable facility to learn some of the fundamental operations necessary for launching space missions from orbit. The new technologies required for rendezvous, orbital countdown, replacement of defective parts, and orbital launch can be worked out. The successful development of such techniques may in turn lead to later generation stations or launch complexes capable, by means of assembly of components in orbit, of carrying out large space missions such as expeditions to Mars. Requirements. I have mentioned that we have made a conceptual space station design based on reasonable research objectives and mission objectives in space to obtain an understanding of the problems involved and furnish our research guidelines. From the research and mission objectives just set forth, and assuming the astronauts' working conditions should be comfortable, efficient, and safe, and that the station should be available within the present decade, we set up the following guidelines. Each requirement represents a problem area on which collectively we have invested much study and research. The results of these investigations form our presentations for this conference. 1. To quickly learn how to live in space and to do the needed research at various gravity levels from 0G to 1G for extended periods, a range of gravity capability is specified. Thus, we sidestep the choice between a zero-gravity station and one with gravity. To digress a moment, a great deal of zero-gravity technology and experience is being built up with the Mercury, Gemini, and Apollo programs. We next need a broader spectrum of experience extending into artificial gravity and continuing zero-gravity research to longer time periods. We fail to see how one can know the best way to live in space without trying both modes of living. The next speaker, Mr. Berglund, who will discuss our configuration research, will show how this objective can be met. 2, I have just shown that a large rotational radius is needed to meet the human factors requirements and to keep the station occupants comfortable. Langley's research on human factors, as derived from experiments on a rotating platform, will be presented by Rolf Stone. 3, because of the large size specified by 2 and the much smaller size required for the payload configuration, it is evident that the station must be erected in space. If this is accomplished by automatic deployment in space, it will be a much easier task than by space tugs. This again puts the burden of the research laboratory, on the research laboratory rather than on the astronaut. This hand model, I don't have the hand model sadly, demonstrates schematically how a rigid wheel-like configuration can be broken into mechanically hinged segments that package neatly in a booster configuration and can be deployed automatically. And I do mean sadly. I wish we had that hand model. That'd be amazing. Mr. Berglund had the basic idea for this configuration. Dr. Buseman worked out the mathematics of this hinge geometry so that there's absolutely no binding. We call this the Buseman twist. The use of a compound hinge, also by Buseman, will be explained by Berglund. 4. Rigid, efficient structures made of space-compatible materials and resistant to meteorites are required for the space station. The rigidity of the structure, the vibration modes, and frequencies depend on both the configuration and structural detail. Mr. Dawson will discuss the structural technology and meteor bumper integration. In case the automatic stabilization system suffers a malfunction, which it surely will, it is important for the safety of the station crew members that the station have an excellent natural stability, so large oscillations will not build up. These would make it difficult to approach the station for docking and even dangerous to abandon ship. I love number 5. I love it because just very straightforward. In case there's a malfunction, and there will be, we need to make sure that it's inherently stable so that large oscillations don't build up and it's safe to approach or leave. I mean, yes, it's a human-built system. There will be a malfunction. I love that they straightforward come right out and say, in case of malfunction, we need a safety, this is the safety requirement, and acknowledges in there, and there will be a malfunction. That's amazing. let's see. It is much easier to understand the dynamics of rotating space stations if one considers the stability criteria outlined in the next slide. The station will be very stable. I don't have the slides right now. Station will be very stable if the moment of inertia about the spin axis is substantially greater than the moment of inertia about the other two orthogonal axes, as in a wheel. The station will still be stable if the moment of inertia about the spin axis is substantially less than about the other two axes, as in a spinning shell. We did see that slide in the glass slides that we looked at earlier. So there's 4 different descriptions of the potential inertias, and in order to describe stability. The shape of the station has a lot to do with the magnitude of disturbances. Cool. Let's see. Number 6. Disturbances of any size infer the need for a damper to damp them out. For space stations, or for space motions, are essentially undamped. And yes, this is referring to inertial dampers as dampers and not as dampeners. And I'm loving that Eric rated just a little bit ago, because when we ran across this concept earlier, I mentioned Eric specifically talking about dampers versus dampeners and the terminological differences, the linguistic difference and lack of uniformity on Star Trek. And here we have a paper from 1962 written by NASA where they are called dampers. I'm not saying that dampeners is wrong. I'm just saying in 1962 at NASA they were referred to as dampers. Control is also needed for orientation. Research with gyro dampers has been particularly successful and will be reported by Mr. Adams in the paper Dynamics and Control. The most controlling factor in the essential environment is radiation, the high-energy particles radiation coming from solar storms and the inner Van Allen belt, the ultraviolet from the Lyman alpha hydrogen line up to the visible wavelengths are of concern with plastic materials and temperature control surface finishes. Our approach to the high-energy radiation problem has been to avoid it by an appropriate orbit selection. With a low orbit inclination of 28 or 30 degrees, the consensus of opinion is that the station would be shielded from all but the Grant solar flares by the Van Allen belt. These have an average occurrence of about once in 4 years. The orbiting altitude of approximately 300 nautical miles, possibly a little lower, is to keep the station below the effects of the Van Allen belt. The eccentricity of less than 1% in conjunction with the low orbit is to keep the station below the Brazilian law of the belt. I don't have time to investigate exactly what that means. I'm unfamiliar with the Brazilian law of the belt. I'm not certain. The vacuum at this altitude to which the materials would be subjected is about 1 × 10⁻⁸ millimeters. It would be nice to have the station turn out to be a DC-3 and gradually become obsolete, but purely a minimum life of a year or greater should be planned for. A damper is a valve or plate that stops or regulates the flow of air inside a duct, chimney, VAV box, air handler, or other air handling equipment, versus dampener, a device that dampens or moistens something. Except that neither of those definitions applies to the use that they're using the term for in this paper. Because they're talking about damping inertia. I think in a similar way to how damper is used with, like, say, regard to airflow in that they're wanting to tamp it down or regulate it, as opposed to dampener, wanting to moisten something. But the audience of Star Trek had no problem understanding when they talked about inertial dampeners. So I don't think either of them is necessarily wrong. One of the other definitions of dampener is to check or diminish the activity or vigor of. So they're like, I'd be curious how long it's had that definition, but yeah, I think both terms are essentially interchangeable in this context. Sonar fade art, I agree. I love the evolution of language. I think etymological research is really interesting, which is part of why I commented on the fact that in this 1962 paper, in the industry that was inventing what Star Trek was, like the industry that it essentially inspired shows like Star Trek, this was an actual term, and in the context of the actual industry, it was damper. But over time, it's become more common to see dampener used in science fiction and in Star Trek, like more modern Star Trek. And I just think that's fascinating. But both terms have appeared in Star Trek. Let's see. Number 8, they want a shirt sleeve environment, which implies excellent temperature regulating system. Calculations indicate that this would be readily possible by means of radiators. However, our first thermal model tests indicated it might be well to bring wool jackets under some operating conditions. A report on our research on thermal balance and temperature control will be given by Clark and LeBand. Another implication of this requirement is that the astronaut should not be obliged to don a spacesuit and go through airlocks from one part of the station to another. 9, the more regenerative the life support systems can be, the less dependent the station is on expensive resupply missions from Earth. The main thing we cannot make regenerative at this time is the food. Langley has a rather thorough research program underway on life support systems and flight type instrumentation, which is supported by 3 divisions. The results and status of this research will be described in the paper entitled Life Support Studies. 10, most NASA research has been on solar concentrators, but almost all of our experience has been with solar cells. A comparison and discussion of power plants will be given by John Dawson and others. 11, booster payload compatibility means the payload dynamics, aerodynamic moments, and buffet characteristics must be satisfactory, as well as the combined aerodynamics and dynamics of the entire launch system. Runyon and Brooks will discuss this compatibility problem as it applies to our conceptual design. 12, leakage rate is the most serious problem with regard to the methods of fabrication and the joining or fastening of parts together. Since a space station has 100 times the surface area of a Mercury capsule, leakage rates must be 2 orders of magnitude or less. Osborne and Goodman will discuss. Okay. The rendezvous and docking requirements are obvious. Also, there should be room in available ferries to evacuate the entire crew in case of an emergency. This, of course, has a bearing on the crew number, docking facilities, and logistic spacecraft available for the job. If we adhere strictly to planned NASA boosters and spacecraft without modification, Apollo vehicles with their capacity of 3 would be the most logical. And it's not overly difficult to dock up to 7 vehicles, which would give a maximum safe crew number of 21. If the vehicles are modified to carry 5, the maximum crew number would go up to 35. Life support for 36 people, 6 per module, have been included in the conceptual design. And with these requirements, we have established the basis for our conceptual design work, which has been the guide to our research program that will be reviewed today. So that was the just a rough draft of space station requirements written in July of 1962. There are pictures. Oh, there's that stability criteria thing that I was like, yeah, we saw this in a slide earlier. This is what it was describing, the different shapes and their stability characteristics. I'm not going to dwell on it because it's in the VOD, or will be. But they built structures of like potential space station things. It's super fascinating, and if we don't get to interstellar flight today, I will do it another day, because I think we're going to run out of time just looking at the space station stuff, and I'm okay with that. This is a mock-up of a mechanically erectable rotating space station at the NASA Langley Research Center in Langley, Virginia. I don't have the control number for this NASA photograph, but it's probably 62 because basically everything else in this set is. Here we have the same mechanically erectable rotating space station at 1/30th. I think it's 1/30th. I wish I had a magnifying glass with me today. I think it's actually 1/50th scale. And then they have the space station hub assembly at 1/10th scale, and docking and parking facilities represented here. Space station rigid module, and you see this little, the little black semi-vertical line there? That's a person. That is a tiny little human form. Because this is illustrating some of the interior of the space station. Ooh, the word dampen was first used in 1547, at least according to Merriam-Webster. But was that the wetness context or the other context? Ooh, same photo, lighter development, but has a caption. Figure 20, right, hub detail of hexagonal station. Upper left, alternate hexagonal configuration. Left foreground, schematic model of H configuration. Oh my gosh. The one here on the the lower left, so this is the H configuration. I don't exactly understand what it's fully illustrating, but you see the tiny little black dot there? The tiny little black line? That is a human, as illustrated on this model. Ricardo, I believe that's what they said, was that it would be the size of the Apollo for deployment. So, and then has to be assembled in space. To check for, oh, really? Okay, so dampen was used in 1547 in the context of diminish the activity or vigor of definition. That spacewalk would be terrifying. I agree. This space station design, I love. So, I assume that many of you have seen the movie 2001: A Space Odyssey. I know, Ricardo, it would be a lot of assembly in space, which is why I like this design. This is not like the final version that I know is in this folder later, but fully inflated torus. So this is a torus design. I believe that some of these models like the design work that is in this folder, I would be very surprised if these were not the space station designs that were used for the station, like, elements of that movie. When they're in the, I don't remember if it's the ship, I guess it's a ship, but whatever. They're in, and it's got the ring, and it's doing the rotation, and it is this work from NASA Langley that was referencing, and the designs they have in the film, I'm fairly certain that they did their research and contacted NASA and were given some of the, like, photographs, because these are the photographs that I have in here that have these NASA control numbers on them. These were like the kind of photos that the press could get a hold of. So movie studios definitely would have been able to get a hold of them. And it actually makes me like the movie more, seeing that, oh, you know, I think they were looking at this stuff when they were designing that. You've not seen 2001: A Space Odyssey. I don't know the last time I watched it all the way through. I tend to fall asleep. So this is the launching configuration for the interrupted Taurus space station, which I guess is the one that we just saw, where it's the, like, instead of like a full Taurus, it was interrupted in points. Let's see. There are some more pictures. It's just so neat. I think this is just really neat. There's a little bit more here about the Manned Orbital Research Lab. MORL. It's just like a bibliography. I'm not gonna do that one. Permeability tester. NASA, Schnitzer, 1962. Gas permeability tester. I guess, so this test, me not knowing for certain, but given the name, I would say this is to determine how easily gas passes through different materials. This adventure is coming to a close. We must return to Earth in 10 minutes. Thank you, Hannah. So that's neat. All of these are neat. I didn't know we had this collection. Yes, we've reached the photos that I saw when I was marking things down for, like, neat. It's Donut Space Station. Inflatable space structure. I do not know if this is a scale model or if... I think this is a scale model. I don't think this is a full-size model. I believe it is a scale model. Here's an illustration of this is what I think they were referring to as the interrupted torus, and the interruptions would be the cinched areas of the torus part of the station, which is inflatable because they wanted the automatic deployment issue. In the requirements, the station, once it got to orbit, needed to deploy itself so that they wouldn't have to do lots of assembly. And their solution for that was to make it inflatable. And it's this kind of thing. It's the torus sort of design that makes me think that they were consulted for 2001: A Space Odyssey. Because there's definite sort of torus design for the stuff in that movie. So the taxi vehicle connecting with the airlock. I don't know, like, this, as far as I know, no inflatable donut space station ever actually got built. Just like the stealth fighter taxi vehicle, I don't think ever was made either. So I think these were like conceptual design of like, this would be grand. And then what we saw earlier, where they were like, but we can do all of this using existing tech in this way. But yeah, it definitely looks like a stealth fighter of some sort, Ricardo. Oh, wow. Yeah. We've got a number of different space station designs. So this is the Douglas configuration, deployed for artificial gravity. So this would be in order to balance the rotation. If I'm seeing everything correctly, this would be the space station module here. These would be solar panels, and it looks like they've got 4 of them on. They've got the 2 Gemini capsules for emergency egress if necessary. And then the like spider's web of connecting cables to connect it to the Saturn IV stage that's used as a counterbalance to then have like the center point of spin be in the middle of those cables. It looks so precarious. And also just amazingly cool, just because I think space is really cool. So same thing, but without the Saturn IV having been deployed for counterbalance. So this is what it would be like when it's up at the top of the rocket. Except the Gemini capsules wouldn't be attached. Those would be those would attach later when they dock after bringing people up to the station, and the solar panels would be inside and not deployed yet. And of course, it would be upright when it's on the launch pad. That's neat. Different version of the Orbital Research Lab with the Saturn IV attached, which from the outside just looks like a capsule. I don't know that we have any internal illustrations. And it looks like we have double prints of a lot of these. Couple versions of the Taurus. Oh. Here, the Taurus station with the fully erected solar collector instead of solar cells, a solar collector, which is just like a giant dish to collect sunlight. With a turbo generator at the bottom, it looks like solar window. So the window would let some sun through, which would be useful for heating the station. Boiler, gimbaled instrument package, and heat storage unit. Neat. 1962. These people were super creative, and this stuff is so neat. There are there's a whole stack of copies of that photo. So, okay. Let's see. The Manned Orbital Research Laboratory. Oh, there's a whole magazine article about it. I don't know, there's some illustrations here with captions. 4. Space station in action. The boom has been bolted in place, and small jets have set the whole station spinning to create artificial gravity, thus eliminating weightlessness. This cutaway shows control and recording centers on the main deck, living and storage areas above, biological lab houses, experimental animals, and algae tanks for growing food. Antennae provide communication with Earth. Men enter and leave by airlock, which seals in the artificial atmosphere. Capsules can cast off for return to Earth. 5. Oh, it is time for stream to end. I'm going to finish real quick. But 5. Training base. Future astronauts will learn how to cope with the environment of space. Here they try free but tethered flight in jet-powered protective suits. 6. Observatory. For studies of weather, the heavenly bodies, radiation, and other matters. Space stations will provide extensively instrumental facilities. Expandable facilities, great, okay. Service stop for the longer trips. To the moon, perhaps, or Mars. These refueling and supply depots will allow lower-powered launchings from the Earth. And 8. Repairs. Unmanned satellites, such as communications relays, may need servicing. Then a rendezvous can be made. Here, space station men check out units. Yeah, I mean, we look at it and these are like expected in like our sci-fi of today, and it's like, oh yeah, sure. You know, space station, it'll be a refueling depot for trips to Mars. But we still haven't gone to Mars. We still haven't gone back to the moon. And we're not, as far as I'm aware, at the moment, planning to use the space station as a refueling depot for that trip. But 1962, they were like, okay, we're going to have a couple of these up there, and they're just going to be like the rest area as you're driving long distance on the motorway. Which is not an inconceivable concept. We just didn't end up moving in that direction. This is the Taurus station. Rather than being an interrupted Taurus, this is just the Taurus station. It's on a boom arm, so that in the laboratory there they can reposition it. So this is the same one that we saw sideways earlier. It's just tilted to a different angle. I thought one of them had a caption, but I don't see it right now. So this part of the station is actually like where the labs and like stuff like that would be located. The inflatable, people would be walking around the inside of that inflatable surface. I remember seeing that. I think maybe I looked up the caption online because I used this image for the promotional image for the episode. So if you give me one moment, I have the caption. I just trying to see all the way over there to the computer that I'm clicking on, which is showing me very, very small. Okay, so NASA photograph L617353, 24-foot large scale model of C. Annulus Taurus erectable space station constructed of Dacron cords and nylon butyl bladder. Date mid-1960. The black and white photograph shows an inflated torus or donut shape held aloft on a metal frame in a warehouse. The torus is slightly lifted from the horizontal with the back angled downward roughly 30 degrees. Black and white thin vertical lines show the pattern all around the torus. There are two white men in suits standing in front of the structure. So the caption is just the 24-foot large scale model of C. Annulus Taurus erectable space station constructed of Dacron cords and nylon butyl bladder. Yeah, this is just really, really neat. But all of these different designs were being tested as means of addressing the requirements that we were reading earlier. And I think their set of requirements made a lot of sense. And so they were just attempting to find the best solutions for those requirements in order to put people up in space for a long period of time. Sadly, that is all the time that we have today for looking through this collection. We did not get to their research on interstellar flight, so I will bookmark that and it will come back in a future episode of Archival Adventures. Also, I will look to see if there's enough on lunar jet transport to do an entire episode, or if I just need to tack that in, like when we do interstellar flight. But that's where we'll leave things for the Paul Hill collection today. I'm going to find a place for us to raid to, and then next week I have, let's see, next week is June 14th, which is Flag Day in the United States of America. It is a holiday here called Flag Day. And because of that, I've pulled materials about the flag of the United States for us to look at some of that history. And then I'm dark for a month. So next week, there is an episode, but then a month off from this show before we come back on the last Wednesday in July. Let's see. All right, we've got a Stephen Joyce who is on. We've got the aviary cam from Monterey Bay Aquarium. And a couple of options. If nobody has a preference, then I'm gonna go where I probably would go myself, which is to say hi to Stephen Joyce, who is a wonderful streamer. Highlights lots of independent games, lots of indie games. Looks like currently about to start playing a game called Grimoire Groves. Also, wearer of tiny hats, and academic who has published on the topic of use of game theory in education and games for education. Just a kind of a wonderful person all around, and we're going to be like saying hi over there. Yeah, hopefully I will see you all again soon. And until I do, keep exploring history, everybody.